and we'll continue. And our next talk, whether Gouri, Mihab, and Benjama are here.
Hello, everybody. I would like to present you my work, which is entitled by Identifying, Modeling, and Numerical Analysis of the Operation of Asynchronous Motor. Next, we have Study and Modeling, and at last we have some results, and we conclude our work. So, let's start with the first part. The pooling of inventors with motors allowed to expand the range of possibilities of the energetic systems. Their optimization can therefore only be carried out correctly if we consider the complete or the whole system motor inventor. The interaction of the motor and inventor is becoming increasingly important, especially for high-speed applications, mainly due to the effect of the inventor modulation on the machine losses. During the operation of these inventors with machines, many problems arise and appear. The allocation of these losses to different components of the drive system needs to be known in order to choose the ideal machine and modulation combination. So, we have here in the second part, motor representation. We consider a machine whose stator is formed by a conventional polyphase winding. The first coil of this winding is supplied by a current I1 of T, periodic of pulsation omega, which can be decomposed into Fourier series, as you see here in Formula 1. The voltage across the same coil is shown in the Formula 2. So, and the inventor representation, the inventor is an important part in the whole system. Machine and inventor or conventor. A conventor supplying a 6-phase machine made up of 2 3-phase machine bridges, bridge A and bridge B, and offset by 30 degrees. During switching between 2 phases, the current depends of the parameters of the motor assembly. Here we have the motor inventor assembly. This is the motor and this is the inventor. We have here 2 bridges, bridge A and bridge B. In this assembly or system, we have 2 parts of shown. In our work, we will try to do our study or to focus in one bridge, which is bridge A. So the figure 2 show current flow during the effective current switching sequence from phase 1 to phase 2. The steady state is established and the course of the sequences is known a priori. The order of succession of operating sequences is steady state is fixed. The current outside the commutations is known. The only unknown of the problem remain the form of the current during the switching sequences as well as the duration of the later. We are going to calculate these quantities. We will then check that evolution of the voltage at the terminals of capacitors as well as that the voltages at the terminals of the diodes and thyristors are such as to allow the planned sequence to take place. Here we have to study and model our system in order to pick up or to find the main problem. The current first part is current calculation during switching. In the first sequence, the current I1 is constant, while it varies during the second sequence. We will call it switching current IC, and it obeys the following differential equations with Formula 3 and Formula 4. We have IC and initial condition IC of 0. We have here differential equations which model the current. And here we have the voltage. The voltage at the terminals of C1 is then equal to the difference between voltages at terminals of the faces of the switching machines, as shown in formula 5 and 6. Sorry. So here we know that IN is the Fourier coefficient of the total current I. IN is given by this formula, as you see here, with condition, initial condition, and also with ICN minus E, or E1 is the sum of known salts. So the modeling of the motor inventor assembly with respect to its harmonics contained the voltage will allow the study of its behavior. This method is based on Fourier series decomposition. As a result here, in our fourth part, at the study of the modeling by Fourier series of motor inventor system was setting up. During the operation of thyrisors, discontinuities of tension or of voltages appear, which raises difficulties in their modeling by the series of Fourier. We have here a Gibbs phenomenon. We have the Gibbs phenomenon. This phenomenon show that we cannot approximate with Fourier series this average. Okay, so trying to solve these problems posed by the voltage jump. We see, as you see here, we have a jump, an average, which is called Gibbs phenomenon. In order to avoid this problem, we try to solve, or we try to find another method or another solution. So following the voltage jump at the end of commutative, the quantity is direct peak onto or tau, which is therefore impractical and possible to approximate by a series of Fourier. So as a conclusion, current and voltage deformation can disturb the normal operation of the inventor motor system and cause malfunctions and perimeter wear of the equipment, in which example the harmonics introduce additional losses and can lead to saturation of the magnetic circuit and thus at a low efficiency. The steady state operation of a machine converter system minimizes harmonic reduction, which serves for a good performance. At last, we have here some references, and thank you for your attention. Is there any questions, or I will be honored to listen some ideas or some about my work and about my problem. Thank you for your attention.
Okay, thank you very much. Let's thank our speaker. It is very interesting, and we wish you good luck in your work.
Thank you,
Thank you very much for your presentation.